So in this video, I'm going to recap some of the basics of performing two-sample t-tests. So let's pretend we have two populations that we're interested in comparing, and if I go back to the example of heights, let's pretend that population 1 is going to be female basketball players and population 2 is male basketball players, and what I want to look at is whether male players are taller than female players. So how I can perform this comparison is I can draw out a sample from each of my populations. So for each of them, let's call this one from population 1 sample 1. They're going to have some size, so the number of observations in the sample, which I'll call N1. We should also be able to measure the average, which I'll call X1, so that's the average height within the sample. And then we should also be able to get the standard deviation of that sample, which I'll call S1. So same thing here, it's going to be sample 2, so it's going to have a size of N2, an average, of X2 bar, and a standard deviation of S2 for the sample. So for my example that I've just done now, what I would say is that HO, my null hypothesis, that's the hypothesis of no change or maintaining the status quo. So if what I was interested in was whether the male players are taller than the female players, then my null hypothesis is going to be that actually they're exactly the same. So if this one has a mean of mu1 and this one has a mean of mu2 for the population, I'm going to say that on average they are equal to each other. So the next thing I need is H1, which is my alternate hypothesis. So this is going to depend on the situation that you're looking at. But say I think that population 2 is taller than population 1, then I could write it like this for H1. Alright, so if I scroll down here, we can start looking at what diagrams we can draw. So if X1 and X2 are normal, so in my example here, X1 and X2 are the heights of people in population 1 and population 2, so they're random variables. So if both of these are distributed normally, then what we can say is the difference in the mean of those sample data is going to be normal as well. So then we know that a normal distribution can be described with both a mean and a standard deviation. So the mean of the difference in means of our samples, so mu x1 bar minus x2 bar, is going to be equal to 0 if we assume that the null hypothesis is true, which is what we do initially. That's because if we look back at this, we could rearrange it. You could say mu1 minus mu2 is equal to 0, okay? And that's what kind of this implies as well. So the other thing that we needed was standard deviation. And we're going to use this as S, x bar 1 minus x bar 2. However, the value of it depends on the assumption that you make for variance that we'll talk about in a second, but you can get a number out for this. So what we can do is draw our distribution of x1 minus x2, which we said was normal, distributed about 0, which we can see here for the mean. And the standard deviation of it, again, depends on this assumption, which we'll talk about in a second. So what we can look at is, okay, we're going to have an actual difference between x1 bar and x2 bar that would have come from our sample data. Okay, so we measured for our sample 1 what the average was, and for our sample 2 what the average was as well. So what we're going to be looking at in terms of our alternate hypothesis is the chance of this happening or something more extreme. So that would be like if we drop a line here, looking for like the probability that sat within this region. So we can calculate what that is in terms of t using this equation here, which follows a very similar pattern to the one for a one sample z-test or t-test as well. So in my example, what I would be looking for is the probability that x1 minus x2 bar is greater than this value here that we got out of our samples. All right, and then we could convert this over into the t-scale. So then we'd be looking at a t-value greater than this calculated t. And of course, this is equal to the p-value, and then you could compare your p-value to your level of significance to decide whether to accept or reject the null hypothesis. So the only other thing then to mention is about this S value. So we said it depends on the assumption of variance. So there's two kind of options that we have. So the first one is to assume that we have equal variance across our two populations, so 1 and 2. If that's the case, you can use this equation to calculate your standard deviation. The other option is that if you assume you have unequal variance across your two populations, 1 and 2, then you have a slightly different equation to calculate your standard deviation, x1 bar minus x2 bar. So you don't need to worry too much about this because Excel will do it for you, but you do have a rule of thumb as to which one you should pick. So you can assume equal variances if this is the variance of the big one divided by the variance of the small one is less than 3. So just remember that for this, variance is equal to your standard deviation squared. Okay, so all you're looking for is the ratio between your two populations' variances, and if it's less than 3, then you can just make the assumption that they're equal. So that's all there is for this recap video, and I'll see you in the example ones.